Greetings, Dr. Nahashima. I, Dashne, number metric B122320095, would like to present our topic assignment, that is the digital signal processing windowing filters. I will start off with the introduction, where digital signal processing plays an important role in modern technology and engineering. It is widely used in communication system, audio and speech processing, biomedical signal analysis, image processing, and control system. This application relies on the DSP techniques to process signals accurately and efficiently. One of the most fundamental operations in DSP is filtering. Filtering is then used to remove unwanted frequency components such as noise, distortion, and interference while preserving the useful information contained in the signal. Digital filters are mainly classified into infinite impulse response, that is the IIR filter, and the finite impulse response, that is the FIR filter. In this project, the focus is on the FIR filter because they are inherently stable and capable of achieving a linear phase response, which is especially important in applications such as audio and image processing, where the signal's distortion must be minimized. However, an ideal FIR filter has an infinite impulse response, which makes it impractical to implement directly. Therefore, approximation techniques are required to obtain a reliable filter. One commonly used approach is the windowing method, which is the main technique used in this project. Next, I'll be explaining the window method and outline objective of this project. The windowing method is used to design the FIR filters by translating the ideal impulse response using the finite length window function. This translation limits the filter length, making the filter suitable for practical implementation. However, the choice of window function has a significant impact of the filter's performance. Different windows influence key characteristics such as the transition bandwidth, frequency resolution, side lobe level, and spectral leakage. In this project, both low-pass and high-pass FIR filters are designed using two commonly used window functions, that is known as the rectangular window and the Hahn window. To evaluate the performance of these two filters, MATLAB simulations are carried out. The analysis focused on the impulse response, which represented the time domain behavior of the filter, and the frequency response, which shows how different frequency components are passed or attenuated. The objective of the project is to compare the advantages and the limitations of the rectangular and Hahn window, and also to highlight the importance of selecting an appropriate window function. As we can see on the next slide, it shows the low pass filter. A low-pass filter, or is known as the LPF, allows low-frequency signal to pass through while attenuating high-frequency components. It acts as a frequency-selective filter that separates useful low-frequency information from unwanted high-frequency noise. In basic electronic circuit, a low-pass filter is commonly implemented using a resistor-capacitor or a RC combination, which helps to demonstrate the basic working principle of the filter. At low frequency, the capacitor has a high reactance, meaning it strongly resists changes in voltage. As a result, most of the input signal is delivered to the output with minimal attenuation. At high frequency, the reactance of the capacitor decreases, allowing high frequency signal to be diverted to the ground, which reduces the amplitude at the output. The cutoff frequency defines the boundary between the passband, where attenuation is low, and the stop band, where attenuation increases as the frequency rises or increases. The role of rate of a low-pass filter depends on the filter order. For example, a first-order low-pass filter exhibits a gradual attenuation slope, while higher-order filter provides a sharper transition between the passband and the stop band. Low-pass filters are widely used in practical applications such as audio system where subwoofers reproduce low-frequency sound and image processing, where low-pass filtering is used for smoothing and noise reduction. As you can see in slide 4 is the image of the rectangular window. The rectangular window is the simplest windowing technique used in digital signal processing. In this method, a fixed segment of the signal is selected and all samples within the windows are treated equally without any form of weighing or tapering. This means that every sample inside the window has the same contribution to the filter design. There is no emphasis or reduction applied to any part of the signal within the window. At the same time, samples outside the window are completely discarded, which effectively terminates the signal to a finite length. This makes the rectangular window easy to be implemented and computationally efficient. One of the main advantages of the rectangular window is the simple design and low computational complexity, which makes it suitable for basic analysis and quick implementations. However, the abrupt edges of the rectangular window introduce signal discontinuities at the boundaries. This sudden transition in the signal lead to undesirable effects in the frequency domain. As the result, the rectangular window produces a high side lobe level which causes significant spectral leakage. This means that the energy from one frequency component spreads into the adjacent frequencies, reducing the frequency selectivity. Due to this characteristic, a rectangular window is commonly used as the reference window when comparing the performance of other window functions such as the Han window rather than the application requiring a high spectral accuracy. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is NURUL NAZIRAH binti HALMI. My matric number is B1224104811. In this presentation, I will explain the time domain characteristic of the rectangular window. Firstly, the rectangular window is one of the simple and most basic window function used in digital signal processing. In the time domain, it has a constant amplitude throughout the entire window duration. This means that all samples within the window are given the same weight with no gradual increase or decrease in amplitude at the beginning or the end of the window. Next, the rectangular window does not apply tapering at its edges. When the window ends, the signal drops abruptly to zero. This sudden change creates sharp discontinuities at the window boundaries. Discontinuities introduce additional high frequency component when the signal is analyzed in the frequency domain. As a result, the rectangular window is more prone to spectral artifact compared to temperate windows such as the Hamming or Han window. Mathematically, the rectangular window can be defined as the given equation in our slide as you can see. This definition clearly shows that all samples in the window are equally weighted. In conclusion, the rectangular window is the simple and easy to implement, making it suitable for basic signal analysis. However, due to its sharp discontinuity, it is less suitable for applications that require accurate spectral analysis. Next, I will explain the frequency domain characteristic of the rectangular window. In the frequency domain, the rectangular window exhibits a sine C-shaped frequency response. This response consists of a narrow main loop and multiple side loops. The narrow main loop provides good frequency resolution, which means it can distinguish closely spaced frequency component effectively. However, the rectangular window also has relative high side loop level. This side loop decays slowly, allowing energy from a dominant frequency to spread into neighboring frequencies. This phenomenon is known as spectral leakage. Due to this leakage, weak frequency components become harder to detect, especially when they are close to stronger frequency component. The effect of spectral leakage becomes more noticeable when the signal does not contain an integer number of cycles within the window length. In such cases, the energy spread more significantly across the frequency spectrum. Mathematically, the frequency domain representation of the rectangular window is given, as you can see in slide. This equation confirms that the rectangular window's frequency response follow a sine C function shape. In summary, although the rectangular window offers good frequency resolution, due its narrow main loop, its high side loop level result in significant spectral leakage, making it less suitable for precise spectral analysis. Now I will discuss the application of rectangular window. The rectangular window is widely used in digital signal processing, especially in spectral analysis and digital filter design. This is mainly due to its simple structure and its ability to provide high frequency resolution when analyzing finite length signal. One common application of the rectangular window is in spectral analysis, where it is used together with the discrete Fourier transform or DFT to convert time domain signal into the frequency domain. The rectangular window is also suitable for applications that require high frequency resolution, particularly when analyzing signal with closely spaced frequency component. It narrow main loop help distinguish this frequency component clearly. Another advantage is its simple structure with uniform weighting, which making it computationally efficient and easy to implement in practical systems. However, due to its abrupt window edges, the rectangular window is prone to spectral leakage. Because of this, it is often used as a reference window for comparison with other window functions such as the HALMI or HAN window. The rectangular window is best suited when computational simplicity is required and the signal content an integer number of period, which help reduce spectral leakage. In conclusion, although the rectangular window has limitations due to spectral leakage, it remains a useful and important window function for basic analyzing and comparison purposes. Lastly, I will explain the characteristic of the hand window. The hand window tapers the signal at the edges using a cosine function. This reduces discontinuities and unwanted high frequency component. It provides better frequency representation with minimal spectral leakage compared to the rectangular window. Firstly, cosine-based tempering edges. Second, reduce boundary discontinuities. Next, minimize high frequency artifact. Next, lower side loop level than rectangular window. Next, good balance between frequency resolution and spectral leakage. Lastly, suitable for accurate spectral analysis. That's all for me. Thank you.
My name is Ahmad FAK'RUDIN with the SULEIMAN. My metric number is B12241045. For the time domain characteristic of the Hans window. The Hans window are smoothly taper the signal amplitude at the start and end. The graduation transition reduces the abrupt change the high frequency component. As the result, signal exhibit smoother time domain behaviors with table 4 frequency analysis. For the Hans window, for the time domain, the amplitude taper graduation at edges provide abrupt transition, reduce the high frequency artifact, provides smoother time domain signal. For the window formula where the yn represent the window function and the n is the discrete time sample index and the n denotes the total length of the windows. The gradation taper prevent the abrupt transition. The are present the reticular window. This is for the Hans window characteristics. Frequency domain characteristic for the Hans window. For the Hans window, in the frequency domain, the response is sync-like, but the some different compared to the reticular window. The main loop slightly wider, which means the frequency resolution is not sharp compared to the reticular window. However, the side loop are much lower. It helps to reduce particular leakage and prevent energy to the spreading to the neighboring frequency. Because of this, the Hans window offers a good trade-off between the resolution and leakage suppression. That's why it's commonly used in the applications such as the audio analysis, vibration management, and the general digital signal processing tasks. Application of the Hans window. The Hans window is commonly used in the digital signal processing to reduce the spectral leakage while still maintaining good frequency resolution. It's a very smooth. The taper edges help reduce sudden transition at the signal boundaries, which is to minimize the unweighted high frequency effect and artifact. Because of this, the strong frequency components are less likely to the much weaker one, making the frequency analysis more accurate. That's why the Hans window is widely used in the application such as the audio processing, filter design, speed analysis, and variation analysis. As you can see the sample for the Hans window. You can see the Hans window and Fourier transform. This is the frequency for the Hans window.
Highlight the crucial differences between the rectangular window and hand window. This is the why behind our choice filter. Main loop width, the rectangular window has a narrow main loop offering the better frequency resolution. And the second point is this is where the different most. The rectangular window has a high side loops leading to several spectral leakage, whereas the hand window has much lower side loop. The third point is rectangular window cause the strong ringing due to their shaped edge. The hand window use a consign-based taper to reduce these effects. Application for rectangular is great for a simple analysis, but hand is industry standard. My name is KHALIDAH Binti Ali. Moving on to the low pass filter design using a rectangular window. In this MATLAB implementation, we already set the sampling frequency at 1000 Hz and the cutoff frequency at 100 Hz. As you can see in the first plot, the rectangular window is very straightforward. It is actually a block to the accurately cut off the impulse response, while this provides a very sharp transition band. It's come with a trade-off. If you look at the bottom graph, you will notice high side lobe level. This causes at we call the ringing effect and or gate phenomena, which can introduce a wanted noise or oscillation into our filter signal. Now, let's look at the high pass filter version. This setup is similar, but here we use a technique called spectral inversion to transform the low pass response into a high pass response. This filter is designed to attenuate everything below 100 Hz and pass the higher frequency. Just like the previous slide, because we use a rectangular window, the transition is sharp, but we still face the issues spectral leakage. This script is particularly useful for a basic education demonstration to show how frequency are blocked or passed based on the window's shape. Let's look at the low pass filter for hand window result when we apply the hand window. Notice the first plot, instead of the sharp box, the window nose has a smooth bell-shaped curve that tapers to zero at the edge. Looking at the frequency response in the bottom graph, you can see that the ripple are significantly reduced compared to the rectangular window, even though the transition band is slightly winded. The overall performance is much better for a real-world application like audio or sensor data smoothing because it is minimize distortion and provide the cleaning output.
Hi, Assalamualaikum. I am Puteri NURFATIN ATIQAH binti FAUZI. This presentation covers the design of a high-pass filter using the hand windowing technique. Based on the MATLAB code, we analyze the sampling frequency of 1000 Hz with a 100 Hz cutoff, applying spectral inversion to achieve high-pass characteristic. The resulting symmetric impulse response confirms a stable linear pass property, while the dominant central peak demonstrates the filter effectiveness. The application of the hand windowing is crucial as it reduces absorb discontinuities and minimizes signal oscillation. In conclusion, this design effectively attenuates frequency below the 100 Hz cutoff, providing a smooth transition band and superior side loop suppression for digital signal processing. Thank you. This slide compares the rectangular window and the hand window. The rectangular window has a sharper transition band, but it produces high side lobes, which can cause more interference. The hand window has a smoother shape, resulting in a smoother frequency response. It also has a better side loop suppression, which helps reduce a spectral leakage. However, the transition band of the hand window is wider compared to the rectangular window. Overall, the hand window is more suitable for application that is require a cleaner and smoother frequency response. Thank you. This slide discusses the analysis of FIR low pass and high pass filter using the rectangular and hand window MATLAB simulation, where are used to study the impulse and frequency response. The rectangular window has a narrow main loop, which give a good frequency resolution, but it has high side loop that cause spectral leakage and the ripple effect. It is suitable for high resolution tasks where a leakage is less critical. The Han window uses a consigned taper, which reduces upstrap, change, and side loop. This results in a smoother impulse response and a less spectral leakage, although the transition band is wider. Window selection depends on the application requirement. Rectangular windows are suitable for simple signal, while Han windows are better for audio, speech, vibration, and interference sensitive application. Thank you. So conclusion, this project demonstrates FIR low pass and high pass filter design using the rectangular and Han window. MATLAB simulation show that the rectangular window offer the high frequency resolution but higher side loop and the spectral leakage, while the Han window provide the smoother impulse response, lower the side loop, and the better stop band attenuation with a slightly wider transition. The choice of a window depends on the application. Rectangular for high resolution and simple computation, Han for minimizing artifacts in audio, noise reduction, or interface sensitive signal. Overall selecting the right window is an assertion for optimal FIR filter performance in the SP application. Thank you.